and I'm so happy to be here. First, when I received the invitation, the title of this conference, Non-Commutative, and in fact, I sent an email and I told them, is it okay for me to participate? And anyway, I end up here, and I notice that not, in fact, there are many talks, they are mixed between commutative and non-commutative, like in the last talk, at least. So anyway, I end up gonna talk about something that I did in 2002. I only have maybe 3 research papers where my rings are non-commutative. One of them is what I'm gonna talk about today, non-commutative rings. Uh, and the good news, I don't remember I ever talk about this paper. So I will share with you what is in this paper uh, now. Okay, I think I can go next. Let's see, what is the thing? How I go next? uh, I'm supposed to press something and I go next. Uh, okay, He- yeah, here it is. Okay, first I want to start with this paper. Uh, I mean, everything is relative, but this is one of my favorite theorem, maybe in the last 10 or 15 years. And the reason, I can give you the reason, when you think about the question, you will think that this question been answered long time ago. And, I was surprised to see that this question is answered completely only in a paper in 2017, 2018. And I get to know about this paper only 3 or 4 months ago. And again, everything is relative, but this is one of my favorite results I have seen in commutative algebra in the last 10 years or maybe more. And look at the answer. The answer is surprising. The polynomial ring over a commutative ring R is a principal ideal ring if and only if R is ring isomorphic to a finite direct product of field. Wow. I mean, this is really kind of so I mean, you know what I mean. Like many of the things we teach or we know become trivial. Like all of us know that the polynomial ring over a field F is a principal ideal domain. Now, the proof of this theorem just by staring at this result, because here n is 1, right? I mean, you don't have to write anything just by staring. If we go and take the polynomial ring with 2 variables, like x, y over a field f, then also by this result, it cannot be principal ideal domain. Why? Because fxy, you think of it as fx, and then you add y to it. And fx definitely is not a field and is not a direct product of fields. So by staring, you are done. And by staring, Zn The polynomial ring over Zn is principal ideal ring if and only if n is square free. Also the proof, nothing, just by staring. So whenever I see this result, this is like really I get excited about this result. It's so beautiful, and the characterization, sorry, and the characterization is very simple. So I'm not sure. Maybe some of you already know this result, but I think I came across that only 3, 4 months ago, and I thought I share it with you. And it was by these two authors, Henry, I cannot pronounce the name, Henry and Lopez, let's call them. It's just beautiful result. Okay, I go to my talk. Okay, my talk, we let R to be an associative ring, not necessarily commutative, and an element E in R, we call it near idempotent if E to the n is an idempotent for some positive integer n. So clearly every idempotent is near idempotent. We define R to be Euler ring if every element of R is a near idempotent. So that means if you choose an x in R, you should be able to find an n so that x to the n is idempotent. Okay, and remember in the Euler, n need not to be the same for all the elements in R. So that make us define what if there exists a fixed positive integer n where x to the n is idempotent for every x, then R we call it exact Euler. So the difference between Euler and exact Euler, Euler for every x there is an n, where x to the n is idempotent. Where exact Euler, there is a fixed n that will work for all the elements in the ring, where x to the n is idempotent. Okay, so what do we know? Okay, here is a remind you with a definition what we mean with an element to be strongly pi-regular ring. An element X is strongly pi-regular if there exists a Y in R and a positive integer n, where x to the n equal x to the n plus 1 times y, and xy equal yx. X and y commute. This is given in this paper, Azumaya, in 1954. So when n equal 1, if n equal 1, this is what we call strongly regular. Okay, so you need to know the definition of strongly pi-regular for this talk. R, we call it strongly pi-regular if all its elements are strongly pi-regular. Okay, here is the first result. Let R be a ring. Then R is Euler if and only if, complete answer, R is strongly pi-regular and the set of unit or the group of units of R is a torsion group. What a torsion group? Each element in the group is of finite order. Okay, so a complete answer to the first question is achieved. R is Euler if and only if R is strongly Piregular and the unit of R is a torsion group. Okay, then I remind you with the definition of what we mean with periodic. What do we mean with periodic ring? Periodic ring means there exists for each x in R, there are integers m and n where m not equal n and x to the m equal x to the n. This is what we mean with periodic. Definitely, if n is equal to m, then all rings are periodic. So, of course, you see why I need m not equal to n. Okay, this kind of periodic rings been studied a long time ago, and I saw a recent paper on periodic rings. And here is the connection between Euler and periodic and strongly biregular ring. So when you say R is Euler, remember Euler mean for every x in R, there is an integer n where x to the n is idempotent. This is equivalent to say that R is periodic, meaning for every x there is an integer, there are integers m and m not equal n, and you have x to the m equal x to the n. And strongly biregular ring, and the unit of R is a torsion group. So these three conditions are equivalent. And of course, remind you again what we mean with a strongly biregular ring. It means for every x in R, there is an n positive integer bigger or equal 1, and there is a y in R where x to the n equal x to the n plus 1, I mean x to the power n plus 1 times y. Okay, so this is, it seems so far so good. We have answers, like we know what we mean with Euler ring. Okay, what about strongly? What about exact Euler? Do we have a characterization of exact Euler? Yes. A ring R is exact Euler if and only if R is strongly biregular and the set of all nilpotent element or the ideal or sorry I should the nil of R, the set of all nilpotent element of R uh, and the group of unit are of bounded index. And what do I mean with bounded index here? That means if x is there is an integer n, there exists an integer n, where x to the n equals 0 for every nilpotent element x. And there exists an integer m where y to the m equal 1 for every unit in R. So nil of R and the set of all nilpotent and the unit are like exactly, that's what we mean with bounded index. There is an n for that work for all the nilpotent, where x to the n equals 0, and there is an m that will work for all the unit, where y to the m equal 1. So far, so good. So this is what we have a complete characterization of exact Euler. Complete answer. Maybe in these two lines here, you see the motivation or why did I call them Euler? Well, in any basic number theory course, we took the phi Euler function. And this phi, all of us know, if you have an a in the integers modulo m, and the GCD between a and m is 1, then a to the phi m is always equal 1, which is an idempotent of the integers mod m. So the question is, replacing 1 is an idempotent. Why don't we just, a to some number equal idempotent? So that, this is the motivation, or that was the line of thinking, in 2002. We were talking about 20 years back. Why I thought of that or that definition. The motivation from this simple number theory that we all study in undergraduate, maybe, or maybe for some of everything is relative. Maybe some of you took it in high school. Okay, well, if you stare at this theorem when R is exact Euler, if and only if R is strongly biregular and the nil and the unit are of bounded index, quickly you think of the integers Zm, because the integers modulo m are definitely strongly biregular and definitely the set of nilpotent, and in this case the ring is commutative, so I can claim the ideal of the nilpotent element, and the set of units are definitely of bounded index. Well, if this is the case, sorry, so here is the result. If you choose an integer m, and of course this is using the factorization of m into product of distinct prime to some power, q1 and qn are distinct prime. All of us know this. Now I choose k to be the maximum of the exponent. K equal the maximum of C1, Cn. Then x to this k here, phi m as you know, the phi function, Euler phi function, is an idempotent. So one way to think of it, I remove this condition, the GCD between a and m is 1. Okay? And like a more general, I don't know if you say more general or we can achieve this result, that whenever you choose k to be the maximum of the exponent, and you calculate phi m, then x to this power is always idempotent. And why? Because the unit of r is bounded by phi m, and nil of r is bounded by k. And the ring is strongly biregular. So by staring by staring at the theorem on the top, that will be the proof of this result. So maybe I should call it corollary or whatever. Okay. By the way, I have 40 or 50 minutes, but I don't think I'm gonna keep you that long. You can have the break before that. But these are ideas I thought I share with you. Here is another definition. What do we mean with unit regular ring? A ring R is called the unit regular ring if for every x in R there exists a unit U where xux equal x. This concept of unit regular ring introduced by Ehrlich, maybe I pronounced the name wrong, in this paper here in 1968. And in the same paper, 1968, he showed that if R is a unit regular ring, and only this condition that 2, the identity plus the identity of the ring, that's what is 2 mean, is a unit, then every element in R is a sum of 2 units of R. And maybe this paper, I think, it's the motivation for many papers after that. I think some of you heard of clean rings and strongly clean rings. I believe they are generalization of this paper in 1968, where each element of the ring can be written as a sum of 2 units. One way, if your ring is a unit regular ring, and 1 plus 1 is a unit. Okay, and then later on in 1976, Fisher, Snyder, Henriksen, in these two papers, they study what they call S2 ring. What does S2 ring mean? S2 ring means a ring R, we call it S2 ring if each element of R is a sum of 2 units. And they study many properties here. They are old papers, but if you are interested, you can find them. Maybe now there is no copyright. Maybe you find them on the net. We're talking about 76 and 74. Okay, in my paper, we define R to be S2 pi ring. So they defined S2 ring. In the paper I'm talking about, we define S2 pi ring. If for each x there exists an integer n, such that x to the n is a sum of 2 units, which is, consistent with the theme of this paper. Instead of x to the n, for each x in R, there exists an integer n where x to the n is a sum of 2 units. A ring R, we call it exact S2 pi ring if you can find a fixed integer n where x to the n is a sum of 2 units for every x in R. So again, the difference between S2 pi ring and exact S2 pi ring is with the integer n. For S2 pi ring, n rely on the element. Maybe different x will have different n. But in the exact, I'm using the same n for all the elements in the ring. Okay? And we achieve this result. Let R be a strongly pi regular ring. Then R is S2 pi ring if and only if every element in the idempotent, that means every idempotent of R is a sum of 2 units. If your ring is strongly pi regular and 1 plus 1 is a unit, then R is S2 pi ring. And here, that's one. The second one, assume R is exact Euler ring. And remember, exact Euler ring means R has to be strongly pi regular ring, and you need the set of nilpotent and the group of units of R to be of bounded index. Okay? Then R is an exact S2 pi ring if and only if every element is a sum of two units. But remember here the hypothesis already that R is exact Euler, which is mean strongly pi regular ring with two more conditions that the set of nilpotent and the group of unit are of bounded index. So you get the same thing. If 2 is a unit, then R is exact S2 pi ring. I think that's all I have in this talk, so you can have a longer break. And I thank the organizer, and I've been in Iran 3 times. One time in IPM, I was invited by Professor Yasimi, and 2 times in Ardabil, I think Muhakkik University. And I have many nice colleagues in Iran that we are still connected. Thank you very much, and I thank the organizer, and that's all I have.